General Maths Unit 2 crew, hello, Taz here. Here's a video for exercise 8b, isomorphic and connected graphs and adjacency matrices. I'm recording this Wednesday, so the day you're actually meant to watch this video, and hopefully this makes sense. By the time I get back, you can always ask questions to get that clarity. So this should be on Google Classroom. Go ahead and see if you can download and print this sheet off, and then I'll go through the video explaining all of the content within here and then go into the example questions, and then towards the end there is a set of questions from exercise 8b that you'll be working on. Question 8 is misleadingly tricky. It looks a bit tricky, but it's actually quite an easy question, so we'll get to that when you see it, you'll have a look and you can see what it's like. So hopefully by now we understand the notion of graphs from last time we looked into it. 8b is going to be looking into this thing called connected graphs and this concept called bridges within a graph. We want to identify what is considered an isomorphic graph, which is a new key term that you'll see pop up a few times, and use what's called an adjacency matrix to represent a graph. So you're going to see graph and matrices go hand in hand and how one can be represented via the other. So a connected graph, if every single vertex, so remember a vertex is like a dot or a little point within a graph, if all of them are connected to every other vertex, either directly or indirectly, it's considered a connected graph. So there's always going to be a one way or another to get from one vertex to another. So all of these graphs here, regardless of whether they have a intersection or not, is considered connected. Where if we have an isolated vertex here that strays away from here, this is not connected because there's no way that we can get to, in this example, vertex B. Same example here. Vertex D is isolated, so we can't travel to it. There's no edge or line that connects to it. Here we have two, it's almost like subgraphs. There's no way that we can get AD to CB. So these ones are considered not connected. A bridge is an edge in a connected graph that, if you remove it, it leaves the graph disconnected. So this particular graph here, graph 1, if you remove the edge from C to D, that will disconnect the graph, leaving graph 2 here. So not all edges within a graph is considered a bridge. There's only a set or a few of them. So imagine if we were to disconnect or remove B and C, there's still a way that B can travel to C via A. So this here is not considered a bridge. Neither is this one, nor is the loop. It's just this specific connection from C to D. This is connected. This connects this side here to this side here. So it's considered a bridge. An isomorphic, also known as an equivalent graph. These graphs contain identical information, and they have the same number of vertices, the same number of edges, and the same connections between these vertices. So even though visually graph 1, graph 2, and graph 3 look different, they're all technically equivalent. The representation of these graphs are the same. So A is connected to D and C, so is here. A is connected to D and C. It's just shown or displayed in a different way. Again, A is connected to D and C. If you go ahead and map out every single vertex connection from one to another, you'll see that all of them will check out. So they're all considered equivalent or isomorphic. Just be wary of if there are any intersections that happen. This can sometimes be misleading, and students tend to think that there's no equivalence between the graphs because of an intersection. This is almost like a redundant piece of information. It doesn't matter if there is an intersection or not, it will still be considered equivalent. And there is a test to see this other than visually. There is a way that you can create a matrix from these and test to see if all the matrices are the same. We'll look into that a little bit down the road. Here are examples of non-isomorphic graphs. you can tell straight away that because there's a connection from D to C here, but there's no connection from D to C here, they're not really isomorphic. There's no equivalence. Okay, so easy to check visually if it's not isomorphic, not as easy if it is, so just be wary of that. Alright, we'll do some examples. So on your sheet, you're going to copy these examples here for A, B, and C. So A is asking which of these three graphs above are connected. I can't necessarily see any isolated section or vertex by themselves. So all are connected in this case. All are connected. Question B, graph 2 contains two bridges. We're going to identify what those bridges are. So the connection from E to D is considered a bridge, because if you remove that, D will be isolated. And also the connection from E to B is a bridge, because if you remove that one, that will isolate ED and A, B, and C. So those are the two bridges. You really got to think about which ones are considered bridges. So you have to almost brute force to see, if I remove this one, will it disconnect the graph? And you might have to trial through every single edge. Question C is asking for the isomorphic graph. So two of the graphs are isomorphic. Identify the isomorphic graph. So which two graphs are considered equivalent? In this case here, it's going to be graph 1 and graph 3. So you can see that these connections A, B, and C are grouped in one way. There's a bridge from B to E, and then D and E kind of has this circular behavior going on, well, in graph 3 anyways. So graph 1 and graph 3 are considered isomorphic. And 3. Now an adjacency matrix is a square matrix. It's always going to be a square matrix that uses a 0 or an integer, 1 or above, to record the number of edges connecting each pair of vertices in the graph. So when we look at each one individually, let's just focus on A. A shows a connection to B one time. So A, read it from here, A to B, there's 1. A to C, there's 1 connection. And A to D, there are 2. 1, 2. So when you represent this in a matrix, you're going to have 0, because A doesn't loop to itself, 1, 1, and 2. If you read the same information down, it's also the same thing, because the connections are two-way. So you'll have 0, 1, 1, 2. You will see this sense of symmetry that happens. And then you just go ahead and do this one by one, marking off every single vertice as you go across. So B has a connection to A, there's 1. B has a connection to C, there's 1. It doesn't loop to itself, 0, and it doesn't connect to D, so it's 0. So you're going to have 1, 0, 1, 0, or 1, 0, 1, 0. If there is a loop, you would put it as a 1, so C to itself has a loop of 1. Just be careful that the degree of this is 2. The amount is 1 when you're putting it into an adjacency matrix. So draw the graph that represents by the following adjacency matrix. So we're going to have 5 different vertices. When you make this, so I'm just randomly putting this in. When you make this, just ensure that you don't have any overlap or intersections, because that will be awesome to interpret it for the reader. I'm going to go ahead and pause this, create this, and we'll see what my result looks like. So your result might look a bit different. It really just depends on how you interpret this information. All right, there we have it. Here it is our graph from our adjacency matrix. It had a little checklist as I was going across. Might look a little bit different. There are no intersections or overlaps of edges, and this suffices as the graph. Here are your questions from 8B, questions 1 to 5. Try doing question 8, see how you go, and then question 9, C, and D. Hopefully I'll see you guys tomorrow at school during community lunch. That'll be awesome. Except for you, Violet, because you probably had to say it right soon. See you guys.